The logarithmic function, or log function, can be written as y equals the log base a of x. And this statement is true if and only if a to the y power is equal to x. Notice that if we flip the positions of x and y there, what we get is a to the x equals y, or just the exponential function, telling us that logs and exponentials are just inverse operations of each other. We maintain the same restrictions on that base a. It has to be greater than 0 and can't be equal to 1. Looking at the graphs below, we can start to perceive that inverse nature between these two functions. What we have graphed here is y equals 2 to the x power and y equals the log base 2 of x. We already know that our exponential function is going to pass through a few key points. -1, 1/2, 0, 1, and 1, 2. If we reflect across that line y equals x, that line of symmetry for inverse functions, then we're going to find those points, those symmetric points, along our line log base 2 of x, or along our curve y equals log base 2 of x. When we reflect across y equals x, those coordinate pairs get flipped, meaning our log function is passing through 2, 1, 1, 0, and 1/2, -1. And then we can start to identify some of the specific characteristics of our log function. In this case, we have a is equal to 2, which is greater than 0. So this serves as a case for, not greater than 0, greater than 1. This serves as a good case for any situation where we have a larger than 1. In this case, we have a domain of 0 to infinity with that open parenthesis at 0, because what we have is a vertical asymptote occurring at x equals 0. Our range, however, will be -infinity to infinity. Notice that those statements are exactly flipped from what we had for exponential functions. Since these are inverses, all of our qualities for x and y get flipped along with it. Our log function will always pass through the points 1, 0, a, where a is that base, 1, and 1/a, -1. And since we have a case where a is larger than 1, we can say that our function is increasing on -infinity to infinity. On the right-hand side, we have, again, y equals 1/2 to the x power, and then y equals the log base 1/2 of x. We still have that symmetric relationship, and what we're going to see are a few key differences. So this is a case where our value for a is between 0 and 1. Specifically, we're looking at a is equal to 1/2 in this case. Our log function is going to be passing through the points 1, 0, 2, -1, and 1/2, +1. We can generalize that to say that our function will always be passing through the points 1, 0, a, 1, where now a is something between 0 and 1, and 1/a, -1. We still have a vertical asymptote at x equals 0, But what's happening is that behavior is changing. Now, since a is between 0 and 1, our function is headed to positive infinity as we approach that asymptote, versus originally, when a was larger than 1, our function was headed to negative infinity. And we can see that since our value for a is between 0 and 1, what we have is a function, a log function, that's decreasing over negative infinity to infinity.